Okay, welcome back, Physics 11. So this week I'm going to start things a little bit differently. Instead of jumping right into the notes, I'm going to ask you a couple of questions that are based on what we learned last week. So this is the first question here. Ball is launched off a platform. You see we got one where it's going straight down, one going straight up, and one going off to the side. Which of these balls is going to have the greatest speed when it hits the ground, A, B, C, or is A going to be the same as B, but they'll both be greater than C, or E, would all of them have the same final speed? So pause the video here and let's try it out for yourself. Okay, hopefully you have paused it and you've tried to solve this out yourself and you've come to the correct answer. So the correct answer in this case is E. They will all have the same speed. Now, if you were to try doing this with kinematics, well, one of the things you could see which might have led you to think of answer D is we know that if you throw something up at 3 meters per second, it'll go to 0 meters per second and then come back down. And when it's coming back down, it'll be going at 3 meters per second. So that's how you can see that B and A will both be passing this point, moving downwards at 3 meters per second. But C is a little bit different. If you wanted to solve this with kinematics, you would have had to follow the same steps we did before. Break it into X and Y components and solve for V final X, solve for V final Y, add them up with Pythagorean theorem, and you'd come up with the final speed being the exact same as you did for part A and B. Now, obviously, trying to do that would be a very time-consuming process. So one of the things I tried to stress on last week's video is we really should be thinking about this in terms of energy. With energy, you don't really care about what's happening in the meantime. You don't care that B is going to go up and then go back down again. You don't have to worry about any of that. You just have to worry about what is my energy at the initial point. So that's when it's being launched down, up, or to the side. And whatever the sum of all those energies is, that's going to be equal to the sum of all the final energy. This is called the conservation of energy principle. So whatever energy you have at the beginning, you're also going to have it at the end. Now, what we should be doing in this case here is when we start these problems, we're going to identify what are the initial forms of energy. So in this case here, they're all starting 2 meters above the ground, so all of them have potential energy. All three of them are starting with a movement of 3 meters per second, doesn't matter the direction, so they're going to have some kinetic energy, and when we add these up, that's going to equal all the final forms of energy. Now in the end, all three balls will be on the ground, and so there won't be any potential, but there will be a final kinetic energy. So, if we break this down into our variables, for potential energy, we remember the formula is mgh. This is going to be 1/2 mv squared for the initial velocity. This is going to be 1/2 mv squared for the final velocity. Now, if we think about all these variables, we know our m is going to be a constant, so that won't change it. We know g is going to be a constant for version A, B, or C. G would be the same for all of those. We know the height is the same for all of them. They all start 2 meters above the ground. And likewise, m is a constant. They all start at 3 meters per second. And so in the end, they're all going to have the same velocity. And I'll leave that for you to try and calculate on your own to see what the speed is going to be for the final speed. So that's the answer for question 1 here, is that E, they're all going to have the same final speed because energy is conserved. Now, let's try problem 2. In this problem here, a ball is just barely rolling off a table, so it starts from rest essentially. It's moving very slowly. We can assume it's starting at rest and falls straight down. This one here is attached to a 1 meter long string, and it's going to swing down. And so which of these is going to be faster when it reaches the lowest point? So again, is the answer C, that both will have the same final speed. So again, pause the video here and try thinking about this problem and solving it for yourself. Okay, if you're just coming back, again, hopefully you were able to solve this one or figure out the answer a bit quicker. This is going to be, again, C, both balls will have the same final speed. Now in this scenario, you are starting with the same amount of potential energy. They're all 1 meter above the ground in part A and B. at the end, they're both they've moved down by a meter. So this was a meter above the ground or above the final position. This was a meter above the final position. So the change in potential energy will be the same. They both dropped by 1 meter. G is a constant and M is a constant. In the end, they're not going to have potential, but they will have kinetic. So that will be 1/2 mv squared. And the M is a constant, M is a constant, G is a constant, H is a constant. So V has to remain the same. So if we compare A and B, all of these variables will be the same. And so that means that V2 will have to be the same when it reaches the final point. Okay, hopefully that is making sense to everyone. So this week is not really going to be a lot of new content. Hopefully you're happy about that. It's just going to be a bit more practice solving these types of energy problems, giving you some step-by-step instructions and a few practice problems. The main bulk of this week's work for you is going to be that lab. So we have a skate park, energy skate park lab that will be on Google Classroom at the same time this video gets posted. So that'll be on Friday, or yeah, that was on Friday. And so I'll try and make this video a bit more brief than last week. So how we solve these problems? The same as we've solved all of our problems, of course. We're always going to start out with a drawing. Now the drawing here, really the main point is to capture the before and after. So what was the situation before, what was the situation after? If we look at these drawings here, we've got our before and we've got our after. Before and after. And likewise here, before, I guess if we wanted to make this an after picture, we would just draw those missing pieces there to show the final picture. So that's the same as before. Now all of these next 5 steps, this is all essentially the information gathering. So what we want to do is we want to determine the initial energy. So we have to think about what are the forms of energy. Now these 3 points here, this is all an idea called work or doing work. Now we're going to worry about these 3 pieces next week. We're not going to deal with them for now, but essentially what if we ignore these 3 points here, we're starting with this principle. The sum of the initial energy is going to be equal to the sum of the final energy. This is for a closed system. So closed system means that no energy is being added to or taken away from the system. So if we consider, say for example, dropping a ball, the ball and the earth might be the closed system. So as long as there's no external force adding anything to that, the initial potential energy the ball has will be equal to the initial kinetic or the final kinetic energy it has when it hits the ground. So that's a closed system. For these 3 points here, this is what we're doing next week. We're kind of thinking out of it this way. The total amount of initial energy plus the sum of all the work being done, energy being added into or taken out of the system, is equal to the sum of the final energy. Okay, but again, this is for next week. So I'm just going to move this to the side for now. Okay, and lastly, we have to determine the final energy. So this is the end piece here. And this is what I was doing in that problem before. You identify what are the initial forms of energy and what are the final forms of energy. Maybe you start out with potential and kinetic and you end with just potential. Maybe you end with just kinetic. Maybe you start with potential and end with some potential and some kinetic. So there's a bunch of different varieties of these problems, but essentially this central part here is going to apply to all of them. This idea here where you're identifying what are these types of energy. So let's go with this problem here. So I'm going to draw the problem out for us. We have a roller coaster starting at rest, traveling down a 45-meter hill, and then back up a 25-meter hill. And what we're trying to find out is, this is our starting point. So remember, for the drawing, we're going to draw where were you at the beginning. So this is our initial conditions. And then where are you at the end of the problem? And this is our final condition. So what it's saying is you start here, so starting as the initial conditions, and we're going to find the speed at the top of the second hill. So this is our final condition at this point. What is going to be our energy? So let's try following the same steps I did before, using the sum of the initial energy equals sum of the final energy. pause the video here and see if you can come up with what is going to be the speed of the roller coaster at this final point here. Okay, if you haven't paused it yet, no cheating. You got to pause the video and try it for yourself. Okay, hopefully everyone's tried it by now, so let's give this a shot. And after I finish this, I'm going to show you a little shortcut to make your life a little bit easier as well. So we start here, you are 45 meters above the ground level, and here you are 25 meters above the ground level. So let's identify what are the initial and final forms of energy. Well, to start with, you are 45 meters above the surface here. So there's definitely going to be some initial potential energy. Will there be initial kinetic energy? Well, if we look at this part here, starting at rest, that means the initial velocity is 0. That means there is no initial kinetic energy. So now let's take a look at the final scenario. Now, in this final scenario, you're 25 meters above the ground, so you're definitely going to have some potential energy there, and you're also going to be moving. And so if you're moving, you're going to have some kinetic energy. So let's break this down. We've got m times g times the initial height is going to equal m times g times the final height plus 1/2 mv final squared. Now, like is often the case, you can see here with these forms of energy, they all have mass involved, and so we can cancel those out. So let's do a little bit of rearranging. So I'm going to subtract g times h final from both sides, and that leaves me with this, g times h initial minus g times h final equals 1/2 v squared. So this gives me 9.8. I'm going to put these two terms together. So I'm going to gather like terms. So g is a constant, so 9.8. And then in brackets, I'm going to have 45 minus 25. That's going to be this value here. So g times 45 minus g times 25 is the same thing as g times 45 minus 25. This is going to equal 1/2 v squared. You know, I'm just going to multiply both sides by 2 here. And so that's going to be 2 times 9.8 times 45 minus 25 equals v squared. And then we can calculate that out. So 2 times 9.8 times, in brackets, 45 minus 25. That's going to equal 392. And that's equal to v squared. And so we're going to take the square root of that, and v equals 19.8. Or, to 2 sig figs, 20 meters per second. Okay, so this is how we can solve this problem, and we can see it's fairly straightforward. You just follow the steps. Now, I did promise you I was going to show you a shortcut to make your life a little bit easier. Now, so this is the one thing that you can do for yourself to make to save you a few steps. So what we did with this problem when we first set it up is we kind of pretended we drew this imaginary line, and we're calling this 0. So this is 0 meters, and that means this is the line where something would have 0 potential energy. And when we did that, this was 45 meters above the line, this was 25 meters above the line, and then we can see that in this step here. We had to take the 45 amount and then subtract the 25 meter amount away from that to give us our change in gravitational potential energy. Well, this 0 line is completely arbitrary. We can put this line anywhere we want. So that's the shortcut that I want to tell you about today, is it's completely up to you where you want to put that line. So why don't I make my life a little bit easier, and why don't I move this line right here? So when I move this line here, you can see, just fix that there, so you can see here that our problem is going to change. Now at this point here, if for the final position, what is the potential energy it has? Well, if this is my 0 mark and it's resting right there, then my final potential energy is just going to be canceled out. And likewise, this over here, it was 45 meters above the ground. I've moved this line up 25 meters. And so now the new difference, I'm going to solve this the second way in green. This is going to be 20 meters above the ground, and this is going to be on the ground level, or on the zero energy level, and this is 20 meters above the zero energy level. So if I solve this here, the only difference I have to make, I'm going to start from this step here, but we're going to carry on using this sort of shortcut here. So I'm going to have g times, let's just leave it as the numbers actually, so I have 9.8 times 20 equals 9.8 times 0, so I'm just going to cancel that out because it's on the ground level, plus 1/2, sorry that's messy, plus 1/2 v squared. So I canceled out the m's in the previous problem. You can see here this becomes 9.8 times 20 equals 9.8 times 0 plus 1/2 v squared. And so again we're going to have the same thing. If we compare this step to this step, we have 2 times 9.8 times 20 equals v squared. Again, we canceled those out last time. So 2 times 9.8 times 20 is the same as 2 times 9.8 times 45 minus 25. So by moving this 0 point, what it allows me to do is essentially it allows me to just cancel out this final potential energy. So I just have initial potential where it's 20 meters above, and final kinetic where it's on the, quote, ground level, or the ground energy or zero energy level. So it does allow us to save one whole term from our calculation. So you don't have to do that, but it's an option for you to save a bit of time. Okay, question 2. You're driving at 35 kilometers an hour, suddenly a road descends 15 meters into a valley, and you step off the accelerator. So you're no longer hitting the gas, you're just going to allow your car to gradually coast down towards the bottom. And so you're moving here 35 kilometers per hour, and then your final situation here is, what is your V final? And more importantly, is it less than 70 kilometers per hour? That's the question we want to know. Is it less than, or are you speeding and you're going to get yourself that ticket? So again, pause the video here, try this problem out for yourself, and come back when you are done. All right, if you're coming back now, here is our scenario. So let's identify what are the forms of energy. We know that this is a true statement. The sum of all the initial is going to equal the sum of all the final. What type of energy do we have at the beginning? Well, it's moving at 35 kilometers an hour, so there definitely is an initial kinetic energy. It's 15 meters above the ground level, and so it definitely does have an initial potential energy. So let's add those here, initial kinetic plus initial potential, and this is going to be equal to the energy we have at the end. Well, it's definitely going to be moving. It'll be moving faster than 35. We don't know how fast yet, but it'll definitely be moving. So there's going to be a final kinetic. Will there be a final potential? Well, no, because we're saying it's at this ground level. So we're choosing this is our 0 meter or 0 joule mark / 0 meter mark, and so there won't be a final potential. All right, let's keep going. We're going to have 1/2 mv initial squared plus mgh equals, and that's the initial height, equals 1/2 mv final squared. And this is what we're trying to solve for here. Again, we can cancel out those m's. They're in every term. If we divide everything by m, those will cancel out. And here's where we would find ourselves here. So v final, I'm just going to do the algebra quickly for us here, is going to equal to 1/2 times the V initial. Now here's the problem. Our V initial is in 35 kilometers an hour. We can't have that, so we got to change that. Now if we, actually we'll just draw it here. So this becomes 35 kilometers per hour multiplied by 1 hour over 3,600 seconds and multiplied by 1,000 meters divided by 1 kilometer. And we're left with, so 35 times 1,000 divided by 3,600. Many of you already just do the shortcut, so take this and divide by 3.6, and this leaves us with V initial equals 9.72 meters per second. So if we take 35, divide by 3.6, 9.72. Okay, so that's what we have over here. So 1/2 times 9.72, let's use the same color, 9.72 squared, plus 9.8 times 15, and we're going to multiply everything by 2 to cancel this out, so times 2 times 2, and so this is what we are going to end up with. So V final is going to be 0.5 times 9.72 squared plus 9.8 times 15 and times that by 2, and then take the square root of that. And this gives us V final equals 19.7 meters per second. Well, we need to know if we're breaking this speed limit in kilometers per hour. So to go from kilometers per hour to meters per second, we divide by 3.6. To go from meters per second to kilometers per hour, we're going to multiply this by 3.6. And that gives us 71. So it's approximately 71 kilometers per hour. So in theory, you could get a speeding ticket. You are going over the posted 70 kilometer an hour speed limit. So there's your answer for number 2. Okay, number 3. Your friend's frisbee is stuck 16 meters above the ground in a tree. Uh-oh. You want to dislodge that frisbee by throwing a rock at it. Now it's stuck pretty tight, so you need to throw that rock pretty fast, at least 5 meters per second when it hits the frisbee. So let's try and draw this out here. So the first thing we should do is draw this out. We've got our tree, and in the tree is a frisbee, flying disc. So we've got this tree up here. Maybe you were playing frisbee golf behind a rock ridge, and this is what happens. So you've got your frisbee in a tree. Now over here you're trying to throw a rock towards the frisbee, and so it says in the question you're going to release it 2 meters above the ground. So this is at 2 meters, and this is 16 meters above the ground. So this is 16 meters. Now you could certainly go ahead and solve this with my initial potential energy being m times g times 2, and my final potential energy being m times g times 16, and in that case you'd have some initial potential and you'd have some final potential. So you can solve it that way, that's totally fine, but we're going to leave it this way. Oh, and by the way, the other piece of the puzzle here is that when it hits the tree, you need to have V final is going to equal 5 meters per second. That's what it says in the problem. It has to be going 5 meters per second when it hits the frisbee. So I will let you solve it. You can try it with doing the 2 and 16, so you do have some initial and some final potential, or you can try the shortcut that we did for question 1. So let's come back in a minute or two, or pause the video, try both of these problems out, and then we'll come back and solve it together. So pause the video now. Okay, now I am lazy, so what I'm going to do to solve this problem is, first of all, I'm just going to change this scenario. So now the rock is being released from the 0 point, and the frisbee is now 14 meters above my above my hand. So instead of saying my hand's 2 meters above the ground and the frisbee is 16 meters above the ground, I'm just going to say that the frisbee is 14 meters above my hand, and that saves me writing one term out. So to answer question 8, does the speed at which you throw the rock depend on the angle at which you throw it? So hopefully you know the answer to that is going to be a strong no. It does not matter. And in terms of your explanation, the reason for that is that as long as whatever path you take, so you could take a path that goes very close to being straight up and lands on top of it. You could throw one kind of straight towards it. Maybe you're standing back further and you want to throw it in an arc like this, something like that. Well, in each of these cases here, it's going to have the same amount of potential energy in the end. It's going to have the same amount of kinetic energy in the end. So that means it's going to have the same amount of kinetic energy at the start. And if it has the same amount of kinetic energy at the start, we know that it's going to have the same velocity at the start. So from this idea that energy is conserved, again, it saves us a lot of hassle, saves us a lot of hard work, because all we need to worry about is the information at the beginning and the information at the end, and what it does in the meantime, what path it takes. Is it going to go up and over? Is it going to go straight from below? What path it takes does not have any impact on it with energy conservation. So let's try solving this here. So the sum of the initial energy is going to equal the sum of the final energy. We identify the types of energy. So because I've changed my 0 point to the point where the rock is when he releases it, I'm not going to have potential energy. It's at the 0 point. So I'm going to ignore that potential energy. If you did 2 and 16 instead of 0 and 14, then you would need to write that down. So based on my method here, I'm not going to have potential, but I will have some kinetic energy. Now in the end, it's going to be 14 meters above my hand, so it's definitely going to have some potential energy, and it's going to be moving at 5 meters per second, so it's definitely going to have some final kinetic energy. And let's break this down. So 1/2 mv initial squared equals mgh plus 1/2 mv final squared. Again, m's, let's just get rid of those. And let's multiply everything by 2. Let's do that at the same time. So this gives me v initial squared equals 2gh plus, well, the 1/2 and the 2 are going to cancel out. So that's going to give me v final squared. I know what v final squared is going to be. I know what g is and I know what h is. So this is going to be 2 times 9.8 times 14 and plus 5 squared, so 25. That's my velocity final is 5, so square that's 25. And now I have 2 times 9.8 times 14 plus 25. That's the total amount, that's equal to v initial squared, and that is equal to, what did we say, 299.4. And so take the square root of that, and what do we have? 17.3. So it doesn't matter what angle you throw it at, but as long as you throw it at some sort of angle where it's going to hit the frisbee, you would need to throw it at an initial velocity of 2 sig figs would be 17 meters per second. So you throw it at that speed. If it hits that frisbee should be coming out of the tree, and you can continue your round of frisbee golf. Okay, one more question for you. Now, if you want an extension activity, you can try this part here, the bonus question. This is going to take you back to your kinematics, your 2D projectile motion. So the question here for the bonus question is how far away is the touchdown point? So what is this distance here? That's going to be the bonus question. So give that a try afterwards if you feel up for it. For the first part here, what we're trying to solve for is what's going to be the speed as she leaves the ramp. So that's the question we're trying to find out. Speed as she leaves the ramp. So what is v at this point right here? So our initial picture is this. Our final picture is going to be this. And what is v final? So pause the video here. Let's follow all the steps that we're going to do to solve for this problem here. Okay, hopefully you've given it a shot here. So again, you have the option of doing two ways of solving this. You can use an initial height of 25 and a final height of 3, or if you're like me, you want to be a bit lazy and save yourself some heartache. So you're going to say this final height is 0, so h final equals 0. I've moved this 0 point to the top of the ramp. I'll draw that very well, but this is going to be the top of the ramp here. And so this is our final height is 0, and that means our h initial is going to be 22. We're just going to subtract that 3 meters away from it. So that's the easy way of solving it. Both are correct. So let's go through and solve it as we do. So sum of my initial energy is equal to the sum of my final energy. Now initially I'm 22 meters above the ground, and she starts out. So what we're going to assume here is meant by this statement here. She just starts at the top. We're assuming that she means starts at rest from the top. So initially we are going to have some potential energy, but we're assuming that there's no kinetic energy. If she was moving, they would have said she's moving with an initial speed of such and such velocity. Now for our final situation here, if you didn't move the 0 point, then she's going to have some final potential and some final kinetic. But if you moved the starting point up the 3 meters, then there's no potential energy. Again, you can cancel out 1/3 of your work. So that's maybe the smarter plan to do, but both are totally fine. So now this is our situation. We're trying to find out the final speed. So we have mgh initial equals 1/2 mv final squared. Let's get rid of those. And we're trying to solve for v final. So 2 times g times h equals v final squared. I've just multiplied both sides by 2 here. And so I have the following. 2 times 9.8 times 22, 22 meters we said. That's going to be the final velocity squared. And so the final answer is going to be 21 meters per second. So V final equals 21 meters per second. That's the final speed there. Now, if you want to solve this for the bonus question here, you can carry on. Essentially what you need to think about is that if this is going down at 60 and there's a 90-degree difference there, then she's going to be launching this way, and this will be 30 degrees. And she'll have an initial speed here of 21 meters per second, or if you want to keep a few more sig figs, 20.77. And so if going at 20.77 meters per second, how far will she go until she touches down? So I'll post the answer here in a second, but if you aren't looking to try that, then you're done the notes for the week. Just keep in mind you do have one homework assignment that will be handed in, and that's going to be the energy lab. So once you finish that, you can just submit it on Google Classroom. Okay, if you're just hanging on for the answer is, for the bonus question here, 43 meters. Okay, that's it for the video, and hope you enjoyed, and we'll see you next week.